Hello everyone, 5.2 transformations of sinusoidal functions part 1. So let's do a little bit of startup here. Can you identify which graph is y equals sine of theta and which is cosine of theta? So a handy skill to have here is be able to recognize these right away. These are your basic sinusoidal functions. So for sine of theta, if I think about it as sine of theta, right? If I say the sine of 0 degrees, so we're in degrees here, right? Well, that equals 0, so I would expect this red graph to be a sine function. So this is sine of theta, y equals. And then if I look at cosine of 0, cosine of 0 degrees, well, we expect that to be 1, which is right here. So this blue graph is our cosine function, cosine of theta, okay? Let's talk about the various transformations of our sinusoidal function. So first is our vertical translation. Okay, it works a lot like our first when we did function transformations. It works a lot. It works exactly like the k value, except here for sinusoidal graphs, a vertical translation is called a vertical displacement, and we use the letter d in each case. Y equals sine of theta plus d, and y equals cosine of theta plus d. If d is greater than 0, the function shifts up. If d is less than 0, the function shifts down. So it works just like the k value for function transformations. The sinusoidal axis is defined by the line y equals d. It represents the midline of the function. So in this case, what is our sinusoidal axis? So let's draw that in. Here's our sinusoidal axis, folks. Let me draw that a little bit better. And I'll draw that in. Let's draw that in green. Okay, our sinusoidal axis is right here, and it's y equals d. So y equals d. Well, in this case, d equals 0 because there's no vertical displacement on either of these two graphs. So y equals d, y equals 0. Okay, so that's our sinusoidal axis. So I'll just write it here, sinusoidal axis at y equals 0. Hey everyone, so we're demonstrating vertical displacement, right? So vertical displacement, also our vertical translation, right? So if I start my standard graph sine of y equals sine of theta, let me overlay y equals sine of theta plus d1, which is the displacement, vertical displacement. Well, what happens when I have a positive displacement, so d equals 1, well, that shifts the graph up by 1 unit. So if I show the new horizontal, so if I show the new midline or the sinusoidal axis, that's y equals 1, well, there it is in the new purple graph, right? So it used to be at 0, then it shifted up 1. So the displacement value determines the equation of the sinusoidal axis. Okay, so that's vertical displacement. Likewise, if we do a negative value, so if I go here, if I go a negative value, well, it's going to displace it down. And the same idea is that our sinusoidal axis shifts down to y equals -1, where it used to be at 0, but now it's at -1. Okay, so that's the sine function with vertical displacement. Folks, same idea with the cosine function and vertical displacement. So here's our standard cosine function. Okay. And then I'm going to overlay y equals cosine of theta plus d2, so the displacement value for cosine of theta. Well, when I have a positive value, it goes up. Okay, and then the sinusoidal axis will go travel up with it. So if I have a d value of positive 2.5, then my new sinusoidal axis will be at y equals 2.5. Okay, likewise, if I have a negative d value for this cosine function, let's say at negative d equals negative 3, then the sinusoidal axis will also shift down to a new equation, y equals negative 3. That's the vertical displacement. Okay, horizontal translation of sinusoidal functions. So for sinusoidal graphs, a horizontal translation is called a phase shift. So this works a lot like our h value. So I'm thinking h value, right? When we did unit 1 with our function transformation. So I'm thinking h value, but here with sinusoidal functions, we call it a phase shift. And instead of using the letter h, we use the letter c. So the form it takes is y equals sine in brackets theta minus c, and y equals cosine in brackets theta minus c. So if c is greater than 0, so it works just like the h value that we know. If c is greater than 0, the function shifts to the right. Okay. If c is less than 0, the function shifts to the left. Okay. Okay. Horizontal translation of sinusoidal functions, also known as phase shift. So if I go to y equals sine of theta, there's our standard y equals sine of theta graph. I'm going to overlay y equals sine of theta minus c1, and c1 is our phase shift value. Remember, when c is greater than 0, right, the function shifts to the right. So I'm going to make c is, right now it's at 0, so it's lined up with our red graph, right? So this is the purple overlaid on the red. C is positive, it's going to shift to the right. So you see the purple line shifting to the right. Okay. When c is negative, c is less than 0, the function shifts to the left. Okay. Couple important things, key things to look at with these sinusoidal functions. Remember, they're repeating. They're oscillating graphs. They're repeating. Well, let's look at some key characteristics, right? So this is in degrees. So you see the x-axis in degrees. What happens when I go to 90 degrees? So let's read the graph here. I'm going to go to 90 degrees to the right, right? So c value of 90. Well, 30, 60, 90, right? So it's out of phase by 90 degrees. So that would be y equals sine of theta minus 90. Okay, what happens when I go to 180? What do you expect here? Look at that. So when there's a maximum in the red graph, y equals sine of theta, there's a minimum in the purple graph. So it's exactly 180 degrees out of phase. So there's a phase shift of 180 degrees. Okay, so when there's a max in one, there's a min in the other. When there's a max in one, there's a min in the other, and so on. Okay, let's keep going. Let's go literally full circle. Remember how I showed you in the beginning where the unit circle, the coordinates on the unit circle, the sine and cosine values, specifically here the sine values in a unit circle, goes around and around in a circle, and it's represented on a Cartesian graph as this oscillating function. So literally when we come full circle, I'm going to go 180 and I'm going to go through it. The other quadrantal angle at 270, there it is. We're 90 degrees away from a full rotation on the unit circle. What does it look like on a sine graph? Let's go all the way. Look what happens with the purple graph. When we're right at 360, we literally come full circle. It matches back in phase, right? So we're back in phase. Okay. When c is less than 0, so let's go back down to 0. So when it's 360 degrees, right? Let's go back. So let's go back to 0. So we're exactly in phase right there. When c is less than 0, what happens? It shifts. There's a phase shift to the left. Okay, and then when we're at 180 degrees, well, same thing, folks, right there. When there's a max in one function, the red one, there's a min in the other. When there's a max in the purple function, there's a min in the red one. Let's go all the way to negative 360. Okay? So remember, unit circle represented on the Cartesian coordinate system all the way to negative 360. Well, we're back in phase, right? So if I start at 0 again, all the way through 360 degrees, we're exactly back in phase. Okay, so that is the sine function. And you're going to expect the same thing for cosine. Let's see here. Okay, there's our classic cosine function. I'm going to overlay y equals cosine of theta minus c2. Well, what happens when I go to the right? Right, when c is greater than 0, phase shift to the right. We go full circle at 360 and matches back to the original graph. When I go to the left, so c is less than 0, so it's a phase shift to the left. When I literally come full circle, again, negative 360, we match graphs again. Okay, phase shifts and relation between y equals sine of theta and y equals cosine of theta. So let's start drawing some conclusions about the relation between the sine function and the cosine function. So for y equals sine of theta, the period is, well, we know this from our investigations, the period is 2 pi. For y equals cosine of theta, the period is also 2 pi. So let's take a look back on our graph here. What's the period? Okay, so when I start here for the cosine function, I go one full cycle. So all the way there, one full cycle comes back down here. So this is 180 degrees. This is negative 180 degrees. So that's 360 degrees. Oops, sorry folks, we're in degrees. So I'm going to keep it in degrees, 360 degrees. Okay, for the sine function, if I start here, that is at negative 30, 60, negative 90 degrees. And then I do one full cycle. Okay, and that is 150, 180, 210, 240, 270, 270 degrees. Well, one full cycle, this is 360 degrees. Okay, and then for the cosine, that's 360 degrees. Okay, so our two periods are 360 degrees. So what are we trying to look at here? Let's take a look at the phase shifts, the out of phase or the phase difference. So sine and cosine functions are out of phase by how many degrees? So out of phase means if I start here with a cosine function, well, it's at a maximum. Where's the sine at a maximum? So pick the reference points that are analogous to each other. Okay, what is this phase difference? 30, 60, 90 degrees. 90 degrees. Okay, so the sine and cosine functions are out of phase by 90 degrees. This is the phase difference. The ratio of the phase difference to the period of sine is, so the phase difference is 90 degrees. So the ratio of the phase difference, so phase difference to period of sine, that's 90 degrees divided by 360 degrees. Okay, or a 1:4 ratio. This will come in handy later when we have to rewrite equations in terms of, like if I give you an equation of a sine function, the classic question is rewrite it in terms of cosine. Or if I give you a cosine function, rewrite it in terms of sine. Well, you have to take into account this phase shift. And then this 1/4 ratio, we'll show you later, will come in handy. Okay, write an equation for a cosine function with a phase shift so that it is equivalent to y equals sine of theta. So when we do this, right, so if my original equation, so in let's see, sine is in red. So if I have y equals sine of theta, well, what is the equivalent equation for cosine? So y equals cosine of theta minus c, right? So what is that phase shift? We said the phase difference is 90 degrees. Well, 90 degrees which way? So take a look. So to go from here to here, that's a phase shift to the right. So here, c is greater than 0. So we're moving to the right. Cosine graph is moving to the right by 90 degrees. So I need to have a positive c value of 90 degrees. So that's minus 90 degrees. Okay? Write an equation for a sine function with a phase shift so that is equivalent to y equals cosine of theta. So y equals cosine of theta. Well, what is the equivalent graph in terms of sine? So y equals sine of theta minus c. Well, what is that phase difference? Well, now instead of going to the right, we need to go to the left. So if I start here, I need to get here to match the cosine graph. So I need to go left and left 90 degrees, right? So when I go left 90 degrees, that's negative 90 degrees. So that's minus 90 degrees. That ends up equaling y equals sine of theta plus 90 degrees. Okay? Make a general statement about phase shifts between sine and cosine functions. So sine and cosine functions are out of phase by 90 degrees or pi over 2 radians. Okay? And you make the adjustment accordingly based on the c value. Okay, demonstrating a sine function and the equivalent cosine function. So remember, they're out of phase by 90 degrees. So if I start with my sine function, okay, and then I have my cosine function here. So if I put that there, right, let me overlay this one where I can change the c value, right? So we said the cosine function is out of phase from the sine function by 90 degrees. Same thing with the sine function is out of phase with the cosine function by 90 degrees. Well, the direction matters here. So if I start with my sine function and then here's my cosine function, well, how do I shift? What phase shift do I have to have with cosine to match the sine function? So what is the equivalent cosine function graph, or what is the equivalent equation for the cosine function to match the sine function? Well, I need to phase shift by 90 degrees. So in this case, it's positive 90. Okay, so there it is. Or if we think about it this way, y equals cosine of theta minus 90. Okay, so before I did that, so watch this. So there's the cosine by itself, right? That's cosine of theta. Sorry. Once I do 90, now it matches the sine graph. Okay, so it's out of phase by 90, so I have to say cosine of theta minus 90 degrees to write the equivalent cosine function that matches the sine function. Okay? Okay, what about the other way? So if I start with a cosine function, okay, and then what is the equivalent sine function? What phase shift do I have to apply to the sine function to match the cosine function? So if I start with, and we know it's out of phase by 90 degrees, but 90 degrees to the left, so I have to do this, right? And you see the sine function matching the cosine function. So another way to look at it is I'll say y equals sine of theta minus, not minus, this time it's plus, and then when I do 90, it matches. Okay, so I have to do a phase shift to the left by 90 degrees. Okay, the graph of y equals sine of x is shown below. Sketch the graph of y equals negative sine of x on the graph. So y equals negative sine of x. Well, I'm going to take some key points here. And then, oh, not that one. Key points here. Okay, and then I'm going to multiply by -1. And I'm going to reflect it, right? So we know that. How do I know that? Well, this is a equals -1, so that's a reflection in the x-axis. Okay, so when I reflect it across, there we go. Okay. Okay, and then let's connect the dots here. There we are. Okay. The value of a in the function y equals sine of x is -1. The a value tells us that the graph of y equals sine of x has been transformed by reflecting it across the x-axis. We know that, okay, from transformations. Let's do some analysis and talk about phase shifts and relation between y equals sine of theta and y equals negative sine of theta. So the original graph and its reflected graph. So for y equals sine of x, the period is 2 pi. So 2 pi. So when we do one full cycle here, red graph, oops, one full cycle, folks, that's 2 pi, okay? How about the reflected graph? For y equals negative sine of x, the period is also 2 pi. So when we look at the reflected graph, well, one full cycle brings us all the way back to 2 pi. So that is 2 pi as well. So the sine and the negative sine function are out of phase by how many degrees? Or how many radians in this case? So this should be radians, folks. Oops, should be radians. Okay, out of phase by how many radians? So if I start at 0 for the red graph, so if I start at 0 for the red graph, right, this point, if I want to match it and make the graphs line up and overlay, well, that's pi radians out of phase, so pi radians, okay? This is the phase difference. The ratio of the phase difference to the period of sine is, so phase difference to the period of sine equals pi over 2 pi, which is just 1/2. This ratio will come in handy later when we're asked to rewrite a sine function in terms of its negative version, negative sine function, or a cosine function in terms of its negative version. We'll do that later on down below. Okay, so write an equation. So let's think of equivalent equations here. Write an equation for a negative sine function with a phase shift so that it is equivalent to y equals sine of x. So if I start with y equals sine of x, what's the equivalent negative version of it. So y equals negative sine of, in brackets, x minus, what's my c value? C equals what? Well, let's take a look. Oops. Okay. When I go from, so I want the negative sign. So let's take a look here. So remember, this graph goes on and on and on like this, right? So if I just extend the axes, and it goes on and on and on like this as well if I extend the axes. Okay, so hang on. So this goes on and on and on, folks, right? So we know this goes on and on and on, okay? And then likewise, I'm just going to extend that red graph like this, right? So there we go. Okay. Then let me just highlight it so it looks, oops, wrong highlighter. Okay, and then the green one, and then the green one. Okay, so let me shift the green graph, and we know it's a value of pi radians, right? Right here, pi radians. That's pi radians from here to here. Well, which way? If I shift the green graph to the right by pi radians, you'll see that this part will line up with this part because these graphs go on and on forever. So we can think of it in terms of a shift of pi radians. So this would be positive pi radians. Okay, so pi radians, and then in this case, minus pi. Well, can we also shift it negative pi radians? What if I start here, right? So let's start here. What if I shift this green graph this way? It will also overlay and line up with the positive sine version, right? Sine function. So we can also think of it as the other phase shift, right? So y equals negative sine of x plus pi. So we can phase shift it to the left. Okay, so how about the other way? So a sine function with a phase shift so that it is equivalent to y equals negative sine of x. So y equals negative sine of x. What phase shift do I have to apply to the positive sine version? So x minus c. So c equals what in this case? We'll go back up. Okay, this time the yellow graph. Okay, this should make sense that it's going to be the same either left or right phase shift by 180 degrees or pi radians to match with the negative version. So if I take the yellow graph here, this part, okay, and I shift it by 100, or sorry, if I shift it by pi radians, which is that much, then it's going to line up. But if I also shift it this way by pi radians, so left or right by pi radians, it will also line up. So we have two options here. So we can either shift it to the left, okay, by pi radians, or we can shift it to the right by pi radians. So make a general statement about phase shifts between sine and negative sine functions. Okay, there is a phase difference of plus or minus pi radians. Okay. All right. Y equals sine of x. There it is. And then when we reflect it, this is, we know that's what it looks like. right? So we're talking in terms of radians here. The reflected graph, y equals negative sine of x, if I replace it with that one so I can vary the c value, it's out of phase by 180 degrees. So remember, I can add 180 degrees or subtract 180 degrees. Well, in this case, I can add pi radians. So pi radians, you can see the blue graphs start to line up. So first, right now it's at 0. And you can see it start to line up. So when I have a positive pi radian, so c is a positive pi, it shifts to the right, and then it lines up, okay, right at about pi. And then I can also go a c value of negative pi, which will shift it to the left, phase shift to the left, and right at about negative pi is where the two graphs line up. Okay, so let me show it with some exactness here. Come on. Okay, so if I just turn that one off, let me turn this one on. Okay, so we know that's the original sine graph. This is the reflected sine graph. I can type in an exact value of pi, so we know that it's in green, right? So I'm going to type in an exact value of pi, and there it is in phase now and lined up with the original red graph, y equals sine of x. Likewise, I can type in negative pi, and there it is. It's lined up as well. Or we can think of it as plus pi, and it's lined up and in phase. Okay, phase shifts and relation between y equals cosine of x and y equals negative cosine of x. Okay, shown is the graph of y equals cosine of x. Sketch the graph of y equals negative cosine of x. So let's do that in purple. Okay, so I'm going to take the key values, and remember, I'm going to reflect them across, right? So that one's about there. That one is about there, there. Okay, you get the idea, right? So okay, let's sketch that in purple. Okay, let's do a little bit of analysis here. Okay, a negative cosine function with a phase shift so that it is equivalent. So write an equation. So we know this. First off, this is y equals negative cosine of x. This is y equals positive cosine of x. Okay. We know that the purple graph is a reflection in the x-axis. Okay. So let's write an equation for a negative cosine function with a phase shift so that it's equivalent to y equals cosine of x. So if I start with y equals cosine of x, and I want to write an equivalent function, that's the negative version. It's asking, well, what is this phase shift? Well, if you're thinking, wow, this is very similar to what we did with the cosine function, well, it's just out of phase by pi radians or 180 degrees. So let's take a look at this. So if I'm looking at this point, okay, if I take this point in yellow, how far apart is this? Well, that's 180 degrees. So they're 180 degrees out of phase. So just like in the sine example, the previous one, it's either positive 180 degrees or negative 180 degrees out of phase. Okay, so a couple ways you can write this. So that's y equals negative cosine of x minus 180 degrees. That is a phase shift to the right, so a positive 180 degrees, or y equals negative cosine of x plus 180 degrees, which is a phase shift to the left. Remember, we can go either left or right. Part 2, a cosine. So write an equation for a cosine function with a phase shift so that it is equivalent to y equals negative cosine of x. So this time I start with y equals negative cosine of x. What's the equivalent function for the positive version? So what is that phase shift? If you're thinking, well, we can phase shift it to the left, or we can phase shift it to the right. Okay, so same deal here. So to the left or to the right. Okay, cosine of x. I'm going to reflect it. Well, there it is, right? Let me overlay this one so I can vary the value of c. So there's the cosine graph, positive cosine function, the negative version, so the reflection, okay? So when I vary the c value, remember I said I can go positive 180 or negative 180 to line it up. In other words, do a phase shift of positive 180 degrees or negative 180 degrees. So I can write an equivalent. So I can write an equivalent equation if I go from the positive cosine. So y equals cosine of x. What's the equivalent version of that when I have y equals negative cosine of x minus c? So what is that c value? So it's either positive 180. So there it is, 180. So you can see it line up perfectly there. Or I go the other way, negative 180. So I do a shift to the left. Okay. First one is a shift to the right. Okay, and then or a shift to the left, and I line up. Okay, so that's another great way to think about reflections, in that it's a phase shift of positive or negative 180 degrees. Okay, example 1. Sketch the function y equals cosine of theta for 2 cycles. So let's do that on the graph. So I'm going to start in black. I know cosine starts right there, so we're in terms of radians. Key points at pi over 6 radians. I know that's square root of 3 over 2. So right there, pi over 3 radians, I'm at 1/2. At pi over 2 radians for the cosine, I'm at 0. Okay, and then the rest, I know the negative versions of these. Oops. Okay, at pi radians, I'm at -1. Okay, and then let's just do a repeating cycle here. Okay, and so on. Let's get 2 full cycles, folks. Okay. Let's make sure we have 2 full cycles here. Is that 2 full cycles? Let me just check with my highlighter. So that's 1 cycle. That's 2 cycles. Okay, so that's 2 full cycles. Let me just draw that in. Okay. That's y equals cosine of theta for 2 full cycles. Okay, let's answer some questions. Next, consider the transform function y equals cosine of theta plus pi over 2 plus 3. Okay, so let's think about the transformations that are happening. So first, couple key characteristics. The amplitude is, well, what's the a value? Well, the a value here is 1, so the amplitude is just 1. And the period is 2 pi. Okay, we haven't changed the period because the b value is just 1, right? So you see the b value there. There's no value there except the number 1, so it's just 2 pi. So, but let's just make sure with, I can measure, start here. Here's the down cycle, here's the up cycle, and back to where I started. That is 2 pi. So if I just look at this carefully, be able to do this at any point. So this is pi over 6, 2 pi over 6, 3 pi over 6. This is pi over 2. And over here, 7 pi over 3, or 14 pi over 6, 15 pi over 6. This is also, 3 goes into 15, 5 pi over 3 goes into 6 2 times, so 5 pi over 2. So the period here, 5 pi over 2 minus pi over 2, that's 4 pi over 2, which is also 2 pi. So the period is still 2 pi. Okay, so I'm going to just clean all that up, folks. Let me just... Okay, you saw that, right? Let me just get rid of that. Okay, so we know it's 2 pi. So you can do that sort of check with the visual check on what the period is. What's the c value? The c value, remember, this is of the form y equals cosine y equals, let me write it on top. Y equals a cosine of b times theta minus c plus d. Okay, we said the a value is 1. The b value is 1, so the period's still 2 pi. What's the c value? The c value here, folks, is negative pi over 2. Okay, c value is negative pi over 2. This represents a phase shift of pi over 2 units to the left. Okay, d equals positive 3. Okay, this represents a vertical displacement of 3 units in the up direction. On the grid above, sketch the sinusoidal axis at y equals. So y equals 3, because my d value equals 3, the sinusoidal axis will shift to y equals 3. So I will put that in red dotted line. Actually, I'll do black dotted line here. Double-ended arrow. Oh no, I want a straight line. Okay, so there's my sinusoidal axis, y equals a positive 3. Use the sinusoidal axis, amplitude, period, and phase shift to sketch the graph of y equals cosine of theta plus pi over 2 plus 3 on the grid above. So first, let me shift everything to the left by pi over 2 units. So pi over 2 units is 3 of these tick marks. So this is pi over 6, 2 pi over 6, 3 pi over 6, right? So we're going to shift every one of these points on the y equals cosine of theta 3 tick marks to the left. So 1, 2, 3. Okay, 1, 2, 3. 1, 2, 3. 1, 2, 3. 2, 3. 1, 2, 3. 1, 2. 1, 2, 3. 1, 2, 3. Okay, so let me just draw this in as we go. Oops. Okay. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, continuing. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 2, 3. Okay, and then let me just draw that in. Okay. Whew. So this one is, oops. This one is y equals cosine of theta. Y equals cosine of theta plus pi over 2. So I shifted it to the left by pi over 2. Okay. Okay. The next part is I need to shift it up by 3. So the sinusoidal axis. So if I take this sinusoidal axis, so let me draw in another one here. Okay, I'll draw it in blue. Come on. Okay, that's the original sinusoidal axis. So that's y equals 0. I need to shift it up to 3. So this entire graph goes up with me by 3. Okay, so what does it look like here? So let's go. So this point goes up 3 units. So 1, 2, 3. So right there. And then this one. 1, 2, 3 units. It's going to get kind of messy. So you get the idea, right? So every point gets shifted 3 units. So the resulting graph is going to look like this, folks. So all the way up here. So up at 4. Right there. And there. Right there. There. Okay, right there. And then here. There. Right there. Okay, and so on. Okay, so the red graph looks like this. This is with that final piece, which is the d value of +3, the vertical displacement of +3. So this one is the final graph, y equals cosine of theta plus pi over 2 plus 3. Okay. What does that look like? So if I go from the black graph, x, y, let's do some mapping notation. That's x minus pi over 2. And then the y value is y plus 3 if we're mapping it. Okay, state the domain and range of y equals cosine of theta plus 2, theta plus pi over 2 plus 3. So domain is x such that x is an element of all real numbers, or in interval notation, there it is. Okay, what's the range? Y such that we're going from a low value to a high value, so 2 to 4. Okay, inclusive, right? So it's y is greater than or equal to 2 but less than or equal to 4. Y is an element of all real numbers. Or in interval notation, square brackets 2 comma 4. Okay, letter D. This is what I'm talking about, equivalent functions, right? Could you write y equals cosine of theta plus pi over 2 plus 3 as a sine function so the graphs would be identical? Well, yes, I can. Let's see. So step 1 would be start with sine y equals sine of x. And of course, writing it out in words is one thing, and thinking about it without a visual, this is hard to do, right? So I'll do this, then you'll see me demonstrate on Desmo so you can see it happen visually, but we should think about it that this is the cosine graph, right? If I think about a sine graph, right, I know a sine graph goes like this. Let's think about it this way, folks. I know a sine graph does this. I'll put this in green highlighter here. Okay, I know a sine graph starts here. Okay, and then it's out of phase by 90 degrees. So pi over 6, 2 pi over 6, 3 pi over 6. So right there. Okay, I'm just going to plot some key points here. Okay, so just so we're straight here, I'm comparing it to the graph in yellow here. Okay, this one. So if I'm doing the sine graph, I'm going to be out of phase by 90 degrees. So 1, 2, 3, 1, 2, 3. Okay, 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, so this is what my sine graph will look like. Okay, so how do I get that green graph to match the red graph? Well, let's take a look at this, folks. Let me just look at this point right here. How do I get that maximum to line up with this maximum? How many units do I have to go to the left? So from this distance, what is this distance? What is that phase shift? So that's starting here. 1, 2, 3, 4, 5, 6. So that's 6 units. That's 6 units of pi over 6. Okay, so that's pi units to the left. Okay, start with y equals sine of x. Okay, phase shift pi units left. So I go from y equals sine of x. I transform to y equals sine of theta. I should do this in terms of theta. Sorry, folks. No. Hang on. Sorry about that, folks. Y equals sine of theta. Phase shift pi units to the left. Okay, so that's y equals sine of theta transforms to y equals sine of theta plus pi. Okay, so that's my phase shift left. Once I do that, once I get this maximum point right here, all I need to do is shift up 3 units. So if I'm here, 3 units, that's at 1.25, right? So this is 1 unit. Oops, sorry. 1.25, 2.25. So 1 unit, 2 units. Oh, shoot, sorry. I'm actually starting here, which is at 1. So 1, 2, and 3 units up. So the last part of this, folks, is y equals sine of theta plus pi. I'm going to transform that with a vertical displacement plus 3. Okay, so this is my equivalent equation. Okay, so this last part was a vertical displacement. Three units up. Okay, or the other way, there's another way to do it, or the second way is first reflect y equals sine of x, so I become y equals negative sine of x, okay? Then translate up 3 units. So let me show this on Desmos, okay? But it should make sense once we... Hey folks, on Desmos, so I start with our base function y equals cosine of theta. I want to transform it to y equals cosine of theta plus pi over 2 plus 3. So I go here, right? First, I know it's a phase shift or translation or a phase shift of pi over 2 units to the left, so negative pi over 2. So I go this way, and that's roughly pi over 2, right? So if I show you in exact terms, that's about where we end up. Okay, and then we said it's a vertical displacement of 3 units up, so I go here with the d value slider all the way to d equals 3. Okay, right there. And then I turn on my sinusoidal axis, and there it is. Okay, so that's how we transform it as we did in our class example. Okay. The other part is how do we how could you write y equals cosine of theta plus pi over 2 plus 3 as a sine function so the graphs would be identical? Well, let's leave this one on. This is the final transformed function right here, right? So let's leave that one up. Okay, there it is. How do I get the sine function? Here's the sine function. How do I get that to match this, right, in terms of sine? So the a value, the part one of this, there's two ways to do it. The a value, we're going to leave that alone. We said first we're going to translate it pi units to the left. So pi units to the left, that's a c value of negative pi. So I'm going to go negative pi. So right there. So initially I was here. And then I'm going to go from pi over 2 to negative pi over 2. See that maximum? It's going to shift so that the maximums are lined up. Okay, so let me make this exact. So that's going to be negative pi. So that's negative pi units. Okay, so now the maximums are lined up. All there's left to do is shift it up 3 units, just like we said in the class example, right there. Okay, turn on my sinusoidal axis, and there you go. That's one way to do it. Okay, let's reset all this, folks. Okay. Okay. Okay, there's my sine graph, right? Remember the other way I said I'm not going to touch the horizontal phase shift, right? So I'm not going to do anything with phase shift, so I'm just going to get rid of that, right? There's no phase shift to be done, so that's just 0. Okay, let's leave it as is. That's still our original sine function. Remember I said we're going to reflect the graph y equals sine of x in the x-axis. So I'm going to go to -1. And so that is what it looks like. Well, what happens when I shift it? Well, now look, the maximums and the minimums are all lined up. So that all that's left to do is do a vertical shift of 3 units up, turn on my sinusoidal axis, and there we go. That's our second way. So so if I do this again, right? Hang on. Okay, so in other words, the a value is -1 and the d value is 3. So if I get rid of this and this, there's our transform function. Okay?